So we are dealing with the third problem in this series, and the third problem in this series is problem number 1.38. The problem is stating a point moves with the deceleration along the circle of radius r so that at any moment of time its tangential and normal accelerations are equal in modulus. At the initial moment t equals 0, the velocity of the point equals v naught. Then find the velocity of the point as a function of time and as a function of the distance covered, and the total acceleration of the point as a function of velocity and the distance covered. So we have a very mathematical question. So this one is a mathematical question and it will involve use of derivative and integration. So let's get started. The problem is giving us an information that AT is equal to AR in magnitude, and it is also mentioned that the point is undergoing deceleration in a circle of radius r such that at t equals 0 the velocity of the point is v naught and it is moving in a circle of radius r. So these are the essential information that is provided to us. So if we begin with this question, so we begin in this way, that AT equals AR. It is a case of deceleration. So we can say that as the particle is moving, it is undergoing a drop in speed, that is minus dv by dt, which is equal to v square upon r. So this is the first mathematical statement which we write, and followed by this we write it as minus dv by dt equals v square upon r. And if we solve this one, we can write it as dv by v square equals dt by r, and then integrating both sides. So at t equals 0, the particle is having a speed v naught, and at a time t it will have a speed v. So on solving this one, we will get the answer for the first part, which is asking us to calculate velocity as a function of time. So minus integration of 1 by v square is minus 1 by v. So minus 1 by v plus 1 by v naught equals t by r. And on adjusting the terms here, we write it as v equals v naught r upon v naught t plus r. So this is the one part of the first problem that we have. Now in this part it is also asking us to find velocity as a function of the distance covered. So as a function of the distance covered, so we again come back to this line that we write again. We are solving the same equation again. So we write minus dv by dt equals v square upon r. Now the problem wants us to solve it in terms of the function of the distance covered. So if we introduce the distance parameter here, so we are using chain rule. So we write this expression as dv by ds dot ds by dt equals v square upon r. Now this is going to be a very interesting line for us to understand. Without this we will not be able to change this expression in terms of distance travelled. Now over here we write this ds by dt term as velocity, and if we do so, we get this expression as minus v dv equals v square upon r multiplied by ds. So if we divide by v square, then we get the expression as minus dv by v equals ds by r, and then integrating both sides. So this time we do not have the upper and the lower limit fixed, so we are integrating it, and we obtain the expression as ln v equals minus s by r, and we are introducing a constant of integration because we do not have the upper and lower limits fixed. Now at the starting of motion, that is at s equal to 0, which is also at t equal to 0, the speed v is equal to v naught. So if we use this expression over here, that at s equals 0, at t equals 0, which is also t equals 0, the v is equal to v naught. So over here we get the constant of integration c equals ln v naught. So this part will become 0, this v will become v naught, so c equals ln v naught, and therefore we can rewrite this expression as ln v minus ln v naught equals minus s by r, and therefore we write it as v by v naught equals minus s by r, and the final answer that we have is v equals v naught e to the power minus s by r. So this is the second part of the first problem which we have discussed. Now in the next part, the problem is asking us to calculate the total acceleration of the point as a function of velocity and the distance covered. Now since it is already mentioned in the problem that the tangential component of acceleration and the radial component of acceleration are same, which we are considering it to be a, which is also equal to v square upon r, and since they both are perpendicular to each other, so we write a net equals at square ar square root, which is equal to root 2a, which is equal to root 2 v square upon r. So in terms of velocity, we have the first answer root 2 v square upon r, and in terms of distance, if we write v as this expression, so we also have a net equals root 2 by r into v naught square e to the power minus 2s upon r. So this is also one of the answers that we have. So this one is one part, this one is another part for the second part of the problem, and this is how we solve this mathematical problem, which is problem number 1.38.